Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Double Integrals over Rectangles. As always, please be an active learner as you watch this video. By way of introduction, and this shows a tumor, and one of the things that medical people are interested in is the volume of a tumor. This is a three-dimensional kind of thing. So in this chapter, we extend the notion of the idea of a definite integral to double and triple integrals of functions of 2 or 3 variables. These ideas are then used to compute volumes, masses, and centroids in physics in more general regions than we were able to consider previously in Calculus 1. We also use double integrals to calculate probabilities when 2 random variables are involved, or even 3 random variables, or more random variables. We will also see that polar coordinates are useful in computing double integrals over some types of regions. In a similar way, we're going to introduce new coordinate systems in 3-dimensional space, namely cylindrical coordinates. I know we talked a little bit about that earlier, not a lot, and spherical coordinates that greatly simplify the computation of triple integrals over certain commonly occurring solid regions. Okay, so this is going to seem very similar to what we did in Calculus 1, except we're doing it in higher dimensions. So in a similar manner, we're going to consider a function f of 2 variables defined on a closed rectangle. So R is a rectangle, and this is the cross product of the closed interval AB times the closed interval CD, and that's the set of xy that are in R2, 2-dimensional space, where x is between A and B and y is between C and D, and that's a rectangle. And here's a picture of the rectangle down here. And we're going to start by saying, as we did when we studied Calc 1, we're going to start talking about f of xy being greater than or equal to 0. We will relax that constraint eventually. So the graph of f then is a surface with the equation z equals f of xy. That's the blue picture here. And we're going to let S be the solid that lies above R, above the rectangle. The rectangle is its base, and under the graph of f. So this is S is x, y, and z, where z is between 0 and f of x, and xy is an element of R. So that's the volume of this thing. Now this surface is curving on top, but the other things are just sides that go up, and again the top is curved. So what we're trying to do is find the volume of that surface S that's not really designated there that way at all. Okay, well, the first step is to divide the rectangle, that's the rectangle down here, into a whole bunch of little slices. Just like when we were integrating over an interval, we divided the interval into a whole bunch of little slices. So we divide this into slices, and just like we picked a point, we pick in each sub-interval, we pick a point in each of these tiny sub-rectangles. And for each of these subrectangles then, and the point that I picked, I put that value for x, in this case it is xij, yij star 0. I put that in the function z equals f of xy, and I get this height. So you see what the area of this then is going to be is this approximating 3-dimensional prism. Is going to be length times width times height, and so you got the area of the little rectangle at the bottom times the height, and I got a block like that. Okay, now if I do that over and over again, what I'm going to get is a whole bunch of these rectangles that I can add them up. And in fact, I can say that the volume is approximately equal to, and this looks very complicated, this is a double Riemann sum, and it would take us a long time to calculate this, but we could calculate this, and the volume would be approximately that, and delta A would be the area of the base for each of those. And so that would be an approach, and our intuition would tell us then that the volume would equal the limit as each of these processes go to infinity. N and M go to infinity of these Riemann sums. And that would be independent of the way I picked these xij's and yij's. If that limit exists, because limits don't always exist, but we're talking about nicely behaved functions, and so we think that limit probably exists. And in fact, this limit right here is exactly what we use as the definition of the double integral of f over the rectangle r. So this is the way we write it. So the double integral, so we have two integral signs over the rectangle r. So r is just written there, of f of xy dA. And notice that we're taking dA here, but the definition of this symbol is, this is the limit as m and n go to infinity of the summation I equal 1 to n, summation j equal 1 to n, f of these points that I picked inside each rectangle times the areas of the rectangles. And by the way, I could pick the rectangles to be different sizes too. As long as the limit exists, that's what we're talking about here. Okay, now there are epsilon delta definitions that you can use. We're not going to concern ourselves with that, but the precise definition would say, given epsilon greater than 0, you want to find a partition of that rectangle such that this number minus that number is less than epsilon, where the partitions are small enough. And we're not going to be focusing on that because my real goal is for you to be able to compute these things. But understand that these are anchored in Riemann sums. We say a function is integrable if that limit exists. And that limit is this limit of the Riemann sums, and I can write it this way. And this is what the definite integral looks like. And notice here I stopped putting those stars on the top and things like that. And it makes sense then that if f of x, y is greater than or equal to 0, then that double integral does have a geometric meaning, just like when we studied Calc 1, we said, integrals, definite integrals have to do with areas. These integrals have something to do with volume, at least when they're positive. So volume is equal to the volume of the f of xy that we're talking about, where it was bigger than or equal to 0. The volume is going to be represented by this double integral over the rectangle R, f of xy, and that's dA, where dA means that we're integrating that Riemann sum that we were talking about. Now, my notes actually have me going through a whole bunch of calculations where I am calculating Riemann sums where m and n are 4. And then I say, oh, what if they're 8? All these calculations, and what if they're 16? This would take probably a full period to do these calculations. And what you kind of see is you start at 41.5 and then you go there, but you're getting closer and closer. And so what you're really doing is this limit is going to exist, and we're doing these Riemann sum approximations to this volume. Now, and it becomes more and more accurate as m and n increases. I'm going to ask you to take that on faith, and since this is a COVID era, that's part of my COVID compromise, is we're not going to do these calculations, but pretend that we did, because we're going to focus on higher powered ways to do these calculations. And so here's a calculation for us to address. If R, the rectangle, is a set of xy such that x is between -1 and 1 and y is between -2 and 2, evaluate this integral over that rectangle. It's the double integral over that rectangle of, this is bigger than or equal to 0. This is the square root of 1 minus x squared, and that is dA. You know what to do. And we're going to see how you do it when we reconvene. So please work on this. But just now more than ever, time is precious. Each day must count. Do the math. It'll make you strong. And now more than ever, take care of yourself and of each other. God bless you until you pick this up again, but we will be continuing with this, and we'll see how you did with that calculation when we get back together.